So welcome in the next video on value function approximation, and in this video we will be talking about deep Q networks. So in the last video we actually introduced the idea of linear function approximation, and we have seen that while in principle it is possible to to approximate any function with a set of linear combination of possibly nonlinear features, we have seen that in practice this is very limited, as it is not easy to actually come up with a good set of features that we can use to approximate the function. And in the end we also discussed why don't we actually replace the linear approximation with nonlinear neural networks. And we said that theory doesn't tell us. Theory tells us that this doesn't work out. But we also have seen that there was early examples, namely TD Gammon, where it actually has been possible to implement that. But the thing is, besides all these few handcrafted and tuned successes of neural networks in reinforcement learning, they have not been managed to be applied as is into reinforcement learning problems. Until actually we have seen DQNs. At the beginning of last century, so it was around 2012, there was a game-changing result published by DeepMind, then acquired by Google, Google DeepMind, that was published in Nature. And what they actually proposed was a single algorithm that can actually be trained on a set of Atari games. There's the Atari 2600 series that consists of 49 games, and they have shown that given a single agent and no special configuration of that agent, they can actually train through reinforcement learning a policy that surpasses the human player in most of the games that are part of this series. The really interesting part of this is actually that they really trained it end to end. So they simply use the images provided by the environment, by the Atari simulator as an input, and there is no pre-processing through the extraction of handcrafted features or something like this, which we have seen in the last video. And in fact, with this contribution, this initiated a round of huge investments, both in reinforcement learning, but also the whole area of reinforcement learning gained a huge push in any directions, including also in research. So on the left side you see, for instance, Breakout, where the very interesting thing I think is that the agent really comes up with the idea to build a tunnel on the left side of the screen. So actually that it actually manages to push up the ball and actually to not having to do anything at all and just getting the points. And here you see a summary of all the different games that are part of the Atari series. Okay, so this is also another summary of this, where you have seen the average. This is like a plot where you see all the games in the Atari series where DQN actually was at or above human level performance, and here below human level performance, also in terms of percentages. So in some of the games actually DQNs really surpassed the human player by more than 300%, 3000%. Okay, so the question is, how does it work? And the basic idea is to use a convolutional neural network that reads the images of the game. We have seen that also in the previous lecture, that it's very important to actually describe the state in a Markovian way, meaning that it encodes everything that is necessary to actually derive behavior from it. So actually describing everything that is needed to actually go into the future. And in this case, we also had the example, if you take a single picture from maybe Breakout in the example above, you will not really see in which direction the ball flies, or with which speed it flies, and also not the velocity of the paddle. And this is why they actually proposed to simply use a frame stack in order to build the markup state manually. So in this case, we just use the four last frames and stack them, and this is our state representation. This is then processed using a convolutional neural network, and the CNN is actually also the function, the value function approximator for a Q function. So in this case, we train all this end to end. We have what we have seen in the last lecture. We define our Q function to take as an input the state S, and we predict all of the available Q values for all the enumerable actions that we can take. So in this example, the state serves as an input to certain convolutional layers. Then we go into, I think, 1 or 2 fully connected layers, and finally in an output layer that provides a linear activation that actually approximates the Q functions for all of the available states. As usually, the reward is the game score, actually, and the network wakes are tuned using backpropagation signals of the reward as is, so there's no special things around it. So actually, and this is actually also what it made it possible to actually train them simply using TensorFlow or PyTorch or Keras or whatever was the framework that was popular back then. But let's maybe dig a little bit more deeper in how DQNs actually work. DQNs usually use, or actually what they use is an objective function that they can use for gradient descent. And this objective function is just our minimization objective. So we have our target in here, and we want to minimize the mean squared error between the target and the predicted Q value. We have seen, if we do Q learning with linear value function approximation, we have defined a feature vector sigma in here, that is actually a phi in here, which is actually linearly combined with a set of parameters. And our target value was actually the Q learning target. So it was the one-step reward plus the discounted maximum Q value of the next state action pair. And then we updated the weights in order to take, in that we took a small step with respect to the parameters in order to reduce our error. And this is very similar also with neural networks instead. So what we here do is we approximate the Q function not through a linear combination of features and a parameter vector, but just using a neural network. And we define our neural network by a set of parameters W. You will see on the next slide why we have different W's in here, but just to be consistent, we simply have the parameters W that define our neural network architecture, and our target value is really simply the same as we have did it in Q learning and Q learning with linear value function approximation, where it is just the one-step reward plus the discounted max Q value of the successor states, which is what we want to optimize. And what we actually do is we optimize our parameter vector, where we take a small step where we actually want to reduce the error with respect. So we actually want to take a gradient descent step that actually optimizes our Q values to actually minimize the difference between the target and the actually predicted Q values. And then with every steps, this is something that has been made clear in the upcoming slides. We actually maintain 2 copies of our neural network, and every k steps we actually copy the state of our current neural network to a frozen target network, which we will introduce in the upcoming slides. Okay, so in order to actually build the intuition behind DQNs and all the tricks that make them work, let's start with a very basic idea of what we're actually doing. So what you see here is the basic agent environment interface, where the agent is somehow like these lower parts, and this is the environment, and it shows our interaction. In standard Q learning, actually what we always do is we have some epsilon greedy policy that takes the argmax action over our Q table or our representation of Q, and we take this action and we get some states back. And in usual Q learning, what we do is we just calculate our target, which is the one-step reward, the one-step discounted reward in here, minus what we currently thought that our Q value was, and we take a small step to actually optimize this. And we keep on iterating, kept collecting samples from the environment, and keep on iterating and reducing our Q-value error. Another simple idea is, why don't we just put a neural network in there? Okay, so this lets us define actually DQN version 0.1. I also like line it out a little bit in here, what we actually get from the environment. So actually, what we get in return from the environment is a state action pair, a reward, and the next state. So this is actually the tuples we also learned from in model-free prediction and model-free control. And if we want to just use a neural network as a function approximator for our Q table, what we just do is actually we take ST at this point, and we actually use this for inference in our neural network. So we predict the Q values for the state ST, which gives us actually the current estimate of our Q values for the action that we actually took. So we take this action, and what we then do is we also have the return that we got from the state. And what we then do is we take the successor state also, and we also make a forward pass with the successor state through our network. And this network then gives us also a set of Q values from which we actually can do the normal Q learning step and actually select the maximum value from it. And then this is all we need. This is then all the ingredients we actually need to define our proper loss function. And the loss function in this step is just being the immediate reward we have as a sample, as a real non-biased, unbiased sample in here, plus the discounted maximum Q value that we got from the second pass through our neural network, minus the original Q value that we also did as we actually before we executed our action in the environment. So this is actually then building up our loss function, and this loss function is differentiable with respect to W, and then we can run a gradient descent step to actually update our neural network parameters to actually come close, so that actually both of these values come close to each other. However, in practice, this does not work and is unstable in training, and this leads to a divergence of the Q values. And the question is, why is that? There is a bag of tricks that actually is performed by DQNs that actually address all these problematic issues. So the first problem is that the experiences that we are actually getting from the environments, they are correlated over time. And as we also, as we keep on doing these two passes through our neural network and we keep on updating Q values near these passes, we are actually running along and keep on updating the network through towards our targets. This actually violates the IID assumption that we also had talked about in the first lecture. And a simple idea to actually break up these correlations that we get from our samples as they are correlated along the trajectory, we just add an experience replay buffer. So the idea is comparably simple, and it was also proposed a long time before, but the idea is just to say we do not do the immediate training step. All the environment samples, all the samples that we get from the environment, what we simply do is we put them in a memory. And every once in a while, we can define it as we want, we randomly sample mini batches of such experiences from this memory. And this has two advantages, by the way. The first advantage, it breaks the correlations as the mini batches are randomized and randomly sampled from this experience replay. Actually, this breaks one of the problematic issues in the IID problems. So this actually reduces the variance. And another thing is actually that we can actually reuse the samples. So there was actually, we also talked about this when we introduced Q-learning. There's this pool sample efficiency as we take these SARS samples actually, and then we use them to update our Q values, and then they throw it away. But this is a lot of data. This is really data inefficient. And if you're really caring about environmental aspects, you want to recycle things. And what you simply can do is you can put them in your memory and you can reuse them for different mini batches. So this increases data efficiency a lot. So what we do, new samples are just added to replay memory, and we randomly sample from this replay memory to actually do our training in the neural network. If we plug this into, so this is still our DeepQ network version 0.1. If we plug this in, what we usually do is, so we keep on doing our loop. Our green loop is actually the execution loop. Our agent running through the environment, taking actions, receiving SIRS samples, which we immediately put into memory. And based on this ST+1 state, we actually put this into our neural network and select with an epsilon greedy policy the action that we will take next. And as a second asynchronous step, actually what we do is we sample a mini batch from our experience replay memory, and we take a pass through our so actually what we do is to build the elements of our loss function. We actually do the two passes through our neural network, one with S1 and one with S2, giving us these two estimate vectors, and these estimate vectors can then be used in an asynchronous way to actually train the parameters W of our neural network with stochastic gradient descent. However, there's one problem still remaining, and this is the problem of the question that arises is how we actually calculate the targets of our Q value. So actually, if we have a function approximator that approximates the Q value, and we do an update based on this loss function, we change both of these estimations because they are really close to each other in their approximation in the neural network. And this is actually really problematic in practice because this also leads to oscillation and divergence during training. This is the problem. So actually it breaks down to the fact that our target Q values that we actually use to calculate the ground truth for our, it's not supervised learning in the case, but the truth that we actually wanna let our Q values converge to, and this is a moving target, and this is really problematic because it also changes constantly with every gradient descent step. And a simple solution for that is to just take two versions of the Q network. This is actually what I had a few minutes ago, where I introduced W to the power of minus in here, and this is actually the idea behind it. In order to having more stable targets that give us our targets that we actually want to converge to with our Q estimates, we want to have stability in there. And because of this, what we do is every n iterations actually, which is usually some higher value, something like 500 or 1000, we actually copy our network, the current state and all the parameters of our network into a second network, which is actually having the same structure. And this is kept frozen while the other network is still dynamic and being updated. However, in this case, the targets, the network that we use actually, so we use actually the frozen network to calculate the one-step transition targets that we want to optimize the values of these values to. So we actually have, basically what this means is we have two sets of parameters for the same network structure, and we have a target network that's actually with parameters V minus, which is slowly being updated with a delay that predicts the Q learning targets in our loss function, and we have a dynamic network that we keep on updating that actually evaluates the current Q values that we also use to run our algorithm and to run our agent. And we always perform a gradient descent step with respect to the parameters W in here. What does this help us technically? The added delay actually breaks the correlations between the Q network and the target networks within the loss function, and this avoids oscillations that we would have this avoids oscillations that we have now fixed targets. The targets are still wrong, but they are fixed over the gradient descent steps in training. Because we actually periodically update the target Q network with copying the weights, we get this delay. And this actually reduces the chance of divergence a lot. So if you want to plug this into our DQN, which was a very unstable version with DQN version 0.2, this now makes illustration a little bit more complicated. So what we now see here, we see the evaluation network and we see the target network. And let's now first consider the top part. The top part didn't change that much. Actually, we still have our agent that uses the current state we're into to actually estimate the Q values and to then use an argmax or an epsilon greedy policy to actually, based on this, select the action to take and to actually execute it. We still also do not directly learn anything. We just keep on receiving this SARS samples and we put them in the memory, from which every once in a while we collect a mini batch of samples to train from. And now here come the complicated parts. We now have a copy of the evaluation network, which is called the target network. And the target network is like a slow and delayed version of the evaluation network, which is only being updated after k timestamps and k being a hyperparameter. However, now in order to actually train our evaluation network in here over this route, we have our loss function in here, and now the loss function uses for these two terms the output of two different networks. So this is our Q-learning target actually, and the Q-learning target is now not derived from the evaluation network, so the upper one that we are actually training, but from the frozen target network defined by the parameters W minus. This is in here. So what we now do is, in order to get our two estimates in here, 1 and 2, we do not perform two forward passes through the evaluation network. We do the forward pass on SY that is actually used to actually get our target. We do this through the target network, and the other one is done through the evaluation network. This gives us then the two Q values, which we can then actually use to calculate our loss function with respect to the parameters of the evaluation network, and then keep on updating the evaluation network using stochastic gradient descent. So these are the main ingredients. There is one further advance of DQNs, which is which is also important to actually make it work, but this is not that generalizable across many other problems. So the general problem also in DQNs was that all the games have different reward structures, and there's larger rewards and lower rewards. And the problem is that large rewards result in large variances in the Q values. And as different games have different reward values, this was problematic to actually get one parameter estimation for one from all the performing well over all the environments. And what we actually want to do is, or the actual problem is, that if you somehow get a reward that is very high by chance, your gradients will be very, very large, and you move your Q values all across the optimization landscape. And the problem is that this is something that you do not want, because this breaks down everything that you have. And the simple idea was just to say, clip the rewards to a range of -1 between 1. So actually you want to go in the right direction, but you do not want to over-exaggerate everything that you're optimizing to. This avoids also oscillation, because you actually normalize the rewards when you train, also when you train multiple games. And actually this prevents Q values from becoming too large than they actually should be. Turns out that the original implementation actually really clips the rewards, meaning that the gradient is 0 at that point. However, in later iterations, they actually defined a different loss function, not the mean squared error, but the Huber loss, that actually can also be derived in a way that these outliers are not weighed so much. And this is actually something very similar to reward clipping, but defining a much more smoother optimization space without the gradients being 0. Okay, so putting all into an algorithm, this is actually what DQNs look like, and it's really also like what you see a lot in reinforcement learning. It's not that much of code that you actually need to write, but you need to write the right code. So actually it's not much, but you need to write it properly. And I mean, it's the same you see, like you run your agent in episodes and you initialize the environment and you get an initial state vector. And then you just keep on running through the environment and keep on incrementing in the time counter, selecting an action in here, execute this action, and also like in here, actually, this is just the evaluation part. You run and you store the transitions in your memory. Then you sample your mini batch of transitions from your memory, and then you define your target in here, and you perform the gradient descent step in there. And every C steps, so this was what I said with K in the previous slides, you update your target network. So this is simply DQNs and actually how they work. And this is also what we ask you to implement in the exercises. So what I also would like to tell you is that DQNs actually were initially proposed in 2012, 2013, 2014, and there has been a lot of progress since then in order to optimize sample efficiency and to keep training being more stable. And I will actually tell you 3 extensions that I think were most relevant to the success of DQNs in practice. First extension is to use double DQN. Double DQN or double Q learning is something that not really has been invented only because DQNs are there. It also was proposed initially for Q learning itself. So the problem is that if you consider the optimization or the target estimation that we actually use for our Q values and we want them to converge to, what you see is actually, or what you see in practice is actually that you get an upwards positive bias of your Q values. So you actually overestimate Q values, and the main reasoning behind this is, so imagine that because we are actually doing function approximation, we have some noise on the predicted or approximated values. And the problem is, in order to derive our Q-learning targets, we always refrain from the maximum Q value that we get from the upward state. And the problem is that if we have an upward bias on some of these estimations, which is clear that we have, this upward bias will actually be part of the target that we actually use to calculate our Q value, to actually want to converge our Q value to. So actually we have an overestimation of Q learning targets, meaning that we train a function approximator that in the end also overestimates Q values. So I think this is a very intuitive reasoning behind it. So the idea is clear that this is problematic. And also originally proposed is to have simply 2 Q functions in order to actually account for the noise that is actually introduced in estimating the maximum Q of the next state, which then results to a bias in our current function approximation. So the idea is to split the selection of an action and the evaluation of an action over different networks. So actually you have 2 networks, and in order to actually resolve this value that you actually need in here and that you calculate, you take the maximum, you take the action that maximizes the Q value from one network, and you evaluate another network and take the value that this action has in the other Q network. And as you think that those 2 networks have different noise inside them, you actually account for the upward noise that you would introduce if you would take the Q value of the actual argmax action from the first network. And turns out that we that we already have two networks in our system. So what we could simply do is to say we use the estimation from our main Q network to select the action, and in order to actually get the value that we are wanting, we use the estimation of the target network for this action, which would then in this network not be the maximum Q value, but the maximum is selected from the one network, and we take the value that is proposed by the other network. And yeah, so there's also like the simple pseudocode for that. This was the originally proposed version of double Q learning, which was already 2010, which is before the introduction of DQNs, but you can like really simply put the idea in, and I think it became mostly clear why this is working in practice. And this is also an idea that you can use for usual Q learning, because there you have also noise in your process and you're updating and bootstrapping your values. So this is something that also helps for tabular Q learning. By the way, feel free, if you implement Q learning using the exercises and you already watched this video, feel free to just plug it in and analyze how much more sample efficient your network will be, and how much faster you actually, not your network, your policy, and how much faster you will actually converge to the optimal policy. If you evaluate DDQNs or double DQN using a subset of the Atari games, what you see here is, by the way, this is the same author, so he actually originally proposed the paper for double Q learning, and also was part of the DQN paper, and also proposed then double Q learning for DQNs. He's part of Udo van Hasselt, it's part of DeepMind. And what you see here is that you see the DQN estimates of over your state space. So actually, and what you see is that if you use the standard DQN estimates, you see that those values are usually much higher than the values you get if you use double DQN. And you also see in here the baselines, which is like the true double DQN, so like the true value that they actually have. And you see that they approach that the blue line really is close to the true value that you would actually want to approximate. And another extension that was also like having a very simple idea, but like gave a big performance boost, was actually to ask yourself, how would you actually sample samples for your mini batch from the experience replay memory? And originally, DQNs proposed to just randomly select a mini batch from your experience replay buffer, and to throw away, also like you define it to have a certain size, and you don't want it to be too much, because actually you learn new samples and you see new areas of the state space. So you want to retain most recent samples longer in your memory, and old samples should go out of the memory. And the idea is also to say, how can you optimize the way you sample from that memory? And the idea is to use an experience, to use a prioritized experience replay memory. And instead of just randomly sampling from your replay memory, you should sample your minimatch based on the absolute Bellman error of the samples that you have in your memory. So actually, if you select a sample in the memory, you can actually plug it into your network and calculate the Bellman error that you have on this sample. So actually, you can calculate how well your value function currently fits to what you have seen so far. And so you can actually define an error per sample, and by this error you can actually prioritize the samples that you draw from your replay memory. And then using these samples, you actually sample from them, and then use them for training, which is something like a prioritization of samples in training, which is also something that you do in supervised learning as well, where you like prioritize the samples where you have largest error on them, that you prioritize them more than the samples that you already can approximate well. So if you're using prioritized experience replay instead of experience replay, what you also see is like this is the uniform DQM, so this is the standard randomly sampling, experience replay, and this is different versions to actually prioritize the sampling. But what you see is consistent outperforming of using the prioritized experience replay over the uniform random sampling from the experience replay memory, which is, I think, somehow also intuitive to understand and gives you a benefit while costing not that much of an implementation effort. And another extension that you also, which is like implemented fairly easily in all of the frameworks, but gives you a huge benefit, is to split your queue networks into 2 different channels. And I think maybe if some of you already trained or are experienced with training neural networks, what you may have experienced if you have a regression target and you want to predict values in the range that should lie between 5 and 6, for instance, your network would be much more accurate if you would train it to predict targets between minus 0.5 and 0.5. And this is something that you account for if you split up the value function. So what we did in the beginning was we just predicted the Q values of the state. So the input was the state, and the output was the Q value of all state action pairs. And what we now do is we say we split the Q value and we distinguish between the state value function, which is actually the value that we can expect from the state, plus and we also predict the advantage. So actually what we do is, in order to calculate the Q function of a state action pair, we want to actually have the value that the state actually has plus the advantage of the action over other actions from that state onwards. And these values are considerably smaller than these values, and they are also like somehow related. And the problem is that if you have like a state value of 600 already, and all your different actions make a minor difference in the Q values, the noise that your neural network will have on all these Q values that you will output will cost you everything, and you will like rank the wrong action over the other action. What you now do is you take this bias out. You say, okay, the state value is given, and I just want to calculate the advantage of the actions over the other actions. And this gives you a much smoother and more accurate ranking. While you can do this like analytically, it is not that easy to do this in an end-to-end fashion into your neural network. But what you saw in this paper is actually to how you actually can approximate this by a special connection of the neurons in your network, and to come up with a loss function that you define with some approximation values alpha and beta. And you can actually come up with an architecture like this, where you, for the state input in here, you estimate the value of the state, and then you estimate the advantages of states of actions over the other actions, and by adding that, which is this one, by concatenating them, you will then get the real Q value. And what you then train is actually different heads on this. So this is basically the 3 main extensions that are part of probably any implementation you will find out there. So if you use, for instance, OpenAI baselines implementation, I think all these 3 elements that 3 extensions that we currently saw are also like activated by default to use them. And now actually the question is, how do they perform actually in combination with each other? And like right after the DQNs have been originally introduced and proposed, there has been a lot of work that actually lines out improvements on them. And at some point, the question was, how can we actually combine them in a rational way to actually outperform everything that was so far? And there has been a paper on that, combining improvements in deep reinforcement learning, where they actually studied the influence of all these elements towards the final sample efficiency on Atari games in this case. And what you see here is you see some baselines, for instance, asynchronous advantage actocritic, so the yellow curve, which is a policy gradient algorithm, which we will discuss in the next lectures. But maybe more like now serving for you as a baseline is the vanilla DQN, which is the gray line in here. And what you see is there is a lot of improvements that by their own leads to a better performance. After all, for instance, what we have seen, the double DQN with the two networks is the purple one in here, which already is a lot of improvement. And there's also noisy DQN in here. This is something that we didn't say, where you really introduce noise in the parameter space, which can be somehow related to, which is maybe similar to what you do with dropout and things like this in supervised learning, where you, through this noise, actually take out variance and actually improve training. And if you combine all these algorithms and ideas together, and if you also define them or configure them so that they really have a good interplay between each other, you can see a lot of improvement this goes much like you would really like stack them all together. This is the final performance, and the final performance is much larger than what you see with vanilla and also with the certain improvements alone. There is also extensions that are not part of standard implementations out there, but they are nevertheless, because actually there's reasons for that, but they are nevertheless important to actually know about. For instance, you might also wonder, or you might be curious about why DeepMind originally proposed to simply stack 4 frames of the Atari frames in order to get the estimate of the hidden state. And the main problem behind this is actually related to partially observable Markov decision processes, where the state that we get from the environment is essentially partially observable and not containing all the information. And what we did in the Atari case is actually that we augmented the state using a stack of subsequent frames to actually build up the Markov state from it. And the question is, why couldn't we simply put these state sequences into an LSTM and use the LSTM hidden state as a state representation? Because actually what an LSTM does is it tries to predict subsequent states, meaning that it implicitly tries to extract the hidden information from the states in order to build a representation from the state that allows for prediction, which is exactly what we want. And actually, this is also working in practice, so you can do this. However, in the reinforcement learning setting, it's not that easy. So if you're not sure what you want to do here, and if in most cases it's easier really to augment the state by stacking it or just augmenting it with other information, unless using an LSTM. So actually it is working, but what usually happens is that you need to estimate much more parameters in your training process, and this additional parameters in your training process usually leads to less sample efficiency in your environment. So usually it's better to augment the state than using an LSTM hidden state for this, but it is working in practice, and you will see also work in the upcoming videos that is actually building on some kind of ideas. So this is actually DQNs. There's a lot of DQN work that is building on top of what we have seen so far, but this is maybe the most important things to know about. If you might now be curious about, hey, isn't this related to AlphaGo, or how is the relation to AlphaGo? Because AlphaGo is also something that comes from DeepMind. I would say AlphaZero and AlphaGo are beyond just extensions of DQN. So the ideas that are behind DQN, they are surely important for AlphaZero and AlphaGo, but we will discuss AlphaGo and AlphaZero in the model-based reinforcement learning lecture, like in a few lectures ahead. And there's a lot of more ideas that actually play into, and we will cover them in the upcoming lectures. So these are a few references and relevant papers. If you're curious, just consider and read them. I think all of these papers that deal with value-based reinforcement learning, and especially these ones, are nicely readable, and it's easy to follow along if you read them.